Okay, here we go with color vision. I erased it while I turned it off. Okay, so color vision, your ability to see colors depend on your ability to build certain cone cells, and the gene happens to be on the X chromosome. Okay, and it tells them that the Y chromosome does not carry an equivalent copy. So females carry 2 copies, males carry 1. Can you come up with a hypothesis? And it kind of gave away a little bit of the information there, but this is a difficult one. So if we look at our table, oops, what number was that? 13. Okay, so if we go back and look at our table, we can see that Jack has normal vision, Jack's mom has normal vision, but Jack's dad is colorblind. Right? So Jack's normal, he's got normal vision, mom's got normal vision, dad is colorblind. He doesn't make the cone type that he needs. And then Jill is actually colorblind, but Jill's mom is not. So Jill's mom's fine, but Jill is colorblind, which is really rare to have a colorblind female. So that should tell them something, right? All right, so looking at 13, they're going to look at that and say, okay, so let's draw out the X and Y. So we know that Jack is an XY. Okay, Jill is an XX. Daisy is an XX. Donald is an XY. Mom is an XX. Now we're told it's on the X chromosome, so we know it's there. And so let's just go ahead and put the label on there. So I'm going to move this. We know she has normal color vision, so we know that at least one of her X's has a good gene. Okay, and I'm actually going to use a big C for color vision. We don't know what her other X is, right? And C is not the best letter, but it's okay. Okay, now Donald, though, he only has 1 copy. Okay, and so as a consequence, he only shows whatever's on there, and he happens to be colorblind, which means that his X has the faulty C on it. Okay, Daisy, she has normal color vision, so we know that at least one of her X's has a good C on it. We don't know about the other one, or maybe we do. Okay, and then if we look at Jack, he's got normal color vision, so we know that his X had a normal C on it. Jill can't see color, which means both of her copies are broken. So she's got 2 little C's. Okay? So if we know that Jill has 2 little C's, and you might actually, I mean, you can ask them right at 13 before you start explaining this, what kind of inheritance is this? If it's on the sex chromosome, it is sex-linked. Okay, on the X chromosome. You can have sex-linked genes on the Y chromosome, they're just much more rare. Because the Y chromosome doesn't carry a whole lot of information. Alright, so if Jill has a little C on both of her X's, well, we know she got one of her X's from her mom. So what do we know about Daisy's other X chromosome? We know that it has a little C on it. Okay? Alright, so that's in number 14. It asks them to fill in the genotypes. That we've done this. Do you know Daisy's genotype? How do you know? Because of her daughter. Do you know Jack's mother's genotype? Do we know what Jack's mother had? We don't. There's no way to know. And it asks, if not, why not? What additional information? Well, you need to see other children, parents, whatever. It's impossible to tell what she has on there. All right? So then for 15, they can go ahead and do the cross. So let's go ahead and do the cross again. All right, so we look at Donald. What possible sperm can he make? Well, he can make a little boy that's going to have the X with the little C on it. Or he can, or a little girl with the X with the little C. Or he can make a little boy with the Y. Okay? And then if we look at Daisy, she has 2 options. She can either give the bad X, or she can, okay, I say bad in quotes, right? Because color blindness is not bad, it's just a defective gene, I guess. Or the big C, okay? So this is going to make a baby girl, and she will be what? She will be colorblind. This is going to make a baby girl. This baby girl, see with C's you're going to have to emphasize that they're different. This baby girl will not be colorblind. Okay, with sex-linked, especially this one, the gene is recessive, so it's a sex-linked recessive gene. Okay, you can have sex-linked dominant genes where whatever the dominant allele is shows up. But in this case, it's recessive. Okay, this one is going to be a little boy, and because he only gets 1 copy, he will be colorblind. And this is going to be a little boy who is not colorblind. So the question is Jill in the offspring? Lo and behold, yes she dang it, we haven't solved it again. Underneath 15 it says, if Donald is not colorblind, would that rule him out as her father? So let's look at that. If Donald had a big C here, is there any way that he can have a daughter who's colorblind? The answer is no, right? Because he has to be able to donate a little C. And so that would have ruled him out, but he's colorblind, so it doesn't rule him out. All right, so then number 16. This is a really weird disease. So this is nail patella disorder. It causes this weird defect where you get these like horns off your pelvis and your nails don't grow, your patella, your kneecap doesn't grow. It's really bizarre. Okay, it's on chromosome number 9. And so we're just going to look at that. And this poor family has nail patella disorder in their family. Okay, so if you go back and look at the table, somebody has it. Let's see. Nail patella disorder, Donald has it, and so does Daisy. What are the odds? So Donald has the disease, Daisy has the disease, no one else does. All right. So I like to let students struggle with this for a second, because let's say that they just assume, like normally people do, that this disease is recessive, okay? And you're going to walk around and just let them assume this. Don't correct them. And you're going to see that, okay, so if it's a recessive disease, then Jack does not have the disease. So he's at least got one dominant gene, right? Jill does not have the disease. She has at least one dominant gene, okay? But both Donald and Daisy have the disease, which means that they are homozygous recessive. Okay, this person does not. If that's the case, can they have Jill? And the answer is no. Yay! We can't possibly have Jill if both parents have the disease. Jill would have to have the disease too. And so I let students get just a little bit excited before I say, oh, darn it, this is an autosomal dominant disease. A what now? Ah, it's an autosomal dominant disease. Now, I like to draw this chart here. So if it's an autosomal dominant disease versus an autosomal recessive disease. Oh, let me do that right. And I say, what are the possible genotypes a person could have? They could have that, this, or this. And this really helps with pedigrees. But, and so I say, okay, this is a person on a pedigree. If we fill them in, they have the disease. If we don't fill them in, they don't have the disease. Okay? So, if these are people and they're diseased, so if it's a dominant disease, any dominant allele is going to show up as a disease. So this person will be diseased, this person will be diseased, that person will be okay. If it's a recessive disease, this person's going to be okay, this person's going to be okay, but this person's going to have the disease. So they look different, okay? So this particular disease is dominant, meaning even one copy is going to give it to you. All right, so let's erase our genotypes, what we thought. Hopefully they did theirs in pencil. Okay, and let's go back and say, all right, if it's a dominant disease, and these people don't have it, so we're going over here. It's a dominant disease, they don't have it, they have to be little a, little a. Whereas these guys have it, so they could be either one of these. They're big A something. Now, we can tell, right? Because if they're big A and he's a, we know that Donald is big A, little a. And we know that mom has a big A because she has the disease, but she definitely has a little a because her daughter does not. So you can totally fill out this table. And so 17 asks, can you fill out the table? Yes. Do you know Daisy's genotype? Yes. Do you know Donald's genotype? Yes. Is it possible for Jill to be the daughter of Donald and Daisy? Now in this case, they don't actually have to do a Punnett square for 17 to answer that question. They can probably see it by now. But is it possible for these two to have this one? And the answer is yes. Darn, yes. So then 18 says, it turns out the nail patella disorder actually is associated with type B blood. And you saw from before that both Donald and Daisy have type B blood. Well, it actually turns out that it's on the same chromosome. So it's on chromosome 9, all right? So we go back to our chromosome picture, just ignore the things there. The type B blood, the B allele, is on chromosome 9, okay? So we remember, if you remember from back there, this is Donald, he was BI. And then the nail patella disorder is also on that same chromosome. So it's just another gene somewhere else on the same chromosome. And it associates with B blood. So we know that Donald is big A, little a. Which of those chromosomes has the big A on it? Well, it should associate with the B. So it's got the big A, and this one's got the little a. This is blood type, so this is I, B, right? Okay. So that's what Donald actually looks like, and Daisy looks the same. So, because Daisy also is, let me make sure, Daisy is also type B blood with the disease. So she looks the same way as that. Now, we don't know whether it's on the pink or the blue. That's impossible to tell, unless you look at parents. But we know that they're on the same chromosome. So on number 18, when it asks you to do this cross, instead of, if they were on separate chromosomes, you'd have 4 possible sperm type, 4 possible egg types. But because they're on the same chromosome, well, when Donald goes to make sperm, he can either give him his blue chromosome, and the sperm will get the B and the big A, or he can give him the pink chromosome, and the sperm will get the I and the little a. There's no other option, right? And we'll talk about in class about crossing over, because there are other options, but right now there's no other option, okay? And same thing with Daisy, because she looks identical. She can either give the big B and the big A, or she can give the little I and the little a, because they're linked. Okay, so that's another genetic term. They are linked, which means they're on the same chromosome. So they're often inherited together. All right, so in this case, what are the possible babies? Well, we're going to have somebody with type B blood and nail patella disorder. We're going to have somebody with type B blood and nail patella disorder. We're going to have someone with type B blood, wow, I sound like a broken record player, and nail patella disorder. Or there's the rare possibility that you could have someone with type O blood, and not have the disorder. All right, so once again, Jill falls plainly into the possible offspring of Donald and Daisy. All right, so with 19, this is where I want you to spend a little bit of time talking about the nature of science. Okay, so 19 says, after all the evidence is in, what should Jack conclude about Jill? Are they half-brother and sister? Now, oftentimes students will, with all the overwhelming evidence, we keep supporting the hypothesis, supporting the hypothesis, supporting the, everything we've done so far has supported the hypothesis that Donald is her dad. And so you might be tempted to say, yep, we've proved it. Donald is her dad. But for some reason with this problem, students don't make that mistake. We do that all the time with other things. Oh yeah, we've proved it. With this, they'll be, wait. We haven't actually proved it. We've just not disproved it. Exactly. So when we're talking about the nature of science and about hypotheses, that's why we never prove anything. Because there's always other possibilities that we haven't thought of. So we haven't proven anything. All we've done is said, oh, it's a possibility, right? That's it. And so have a little discussion about that. And then, what was I going to say? So then what's the next step, right? So here Jack still has got this problem. Can he marry Jill or not? And you're going to tell the students, well, we'll find out later. Because we can do DNA testing. We can swab the cheek. He's just going to have to bite the bullet and ask for a DNA sample. And we're going to learn in a later lab how to interpret that DNA sample. And so we'll find out. And of course the students are mad that they can't find out now, but then you get to choose actually as the TA whether to disappoint them or make them happy. So you can choose that in a later lab, and I'll talk about that later. I'm going to pause this for a second and then we'll go through the homework.